Okay, welcome. This one's an extension PowerPoint. This is information about the atomic model that takes the whole idea a bit further. Because some of you will be asking much more, and I'll probably talk about it in class anyway, but you probably want to know more, I'm sure. So, I'm going to look at this idea of the atomic model and how it was developed. Talk about this idea of mass and charge with our protons, neutrons, and electrons, which we've already done. But also this idea of alpha, beta, and gamma radiation particles, because these things become unstable. So some of you may have been asking these sort of questions. Some may like to go a little bit deeper and just find out more about this sort of stuff. This is a little opportunity. So, all matter, made of atoms. Element, a substance that only made of one type of atom. So here's our lithium again, although it's actually incorrect, because there's 4 green and 4 red in there, but only 3 blue. So I should have chosen that diagram. I just noticed it then. I should have 4 blue electrons. So it should be beryllium. Anyway, each element has a particular letter symbol assigned to it. Normally it's derived from its English name. So carbon, capital C. Copper, that's already taken. It actually got capital C lowercase u, because the original name was cuprous from Latin. So copper's Cu. Cobalt, Co. The C's already taken. We're using its English name. So capital C, little o. As you'll see, there's about a dozen that are from either Latin, Greek, or Wolfram from Old German for tungsten. Anyway, so there's a naming system. So essentially the Greeks were the first to put forward an idea of a particle that couldn't be divided any further. So atomos means unable to divide. It was Democritus and Leucippus, I think, from memory. And that sat there for a long time, not being looked at much until John Dalton started to try and make some models of this. So he decided that all atoms consisted of individual particles called atoms. An atom of the same element was alike, so stuff that we still know. Atoms could not be created or destroyed, which is sort of true, although in a nuclear reaction we do tend to destroy them. Atoms combine in simple ratios to form molecules. So this is John Dalton. We're talking 1700s. This is stuff we still use. He was quite clever in that sense. And then J.J. Thomson, a little bit later than Dalton, proposed this idea of the plum pudding model. And so, while Dalton didn't have a picture in his head of how this looked, Thomson created this plum pudding. So here's our electrons, the plums, in this big gaseous positively charged space. So at that point in time, we really only had electrons. A rather clever character, a New Zealander, Ernest Rutherford, really wanted to try and work out what was going on. So he started scattering things called alpha particles into pieces of gold foil, so very fine gold material. And he decided that really the atom's mass must have a really concentrated center, just by the way these alpha particles bounced off them. So he decided there's a little dense thing called a nucleus in the middle, and a lot of space around the outside. So here's his experiment there. He's got his little lead box. A radioactive source is probably pitch blende or something in those days, which were full of radioactive metals. And then another lead screen. So he's trying to cause a beam of alpha particles that are falling off this to then hit his gold foil. And he had these screens that would allow him to see where the alpha particles ended up. And to his surprise, many would bounce off, coming forward. That probably didn't surprise him too much. He expected them to hit something. But lots of them were going straight through. And others were going in and bouncing off at angles. This is why he decided that he must have a central nucleus, but most of this substance, this piece of gold, was in fact empty space. Which is weird when you think about it, because that means really you're just like a lot of empty space too. We don't sense it though, do we? Niels Bohr then developed a more complex model. He started to put together all the information that they had and decided that we have this nucleus that contained positive particles called protons, and we had electrons that were whizzing around the outside and they were negatively charged, therefore they were attracted to that positive center. And he called these shells of energy. The first shell has 2 electrons, 1, 2. This second shell is showing it having 2 levels of energy in it. We've got 1, 2, 3, 4, 5 in there, so we've got 7 electrons. 1, 2, 3, 4, 5, 6, 7 protons. Good. So we're looking at nitrogen. I'll teach you how to do that. And then this guy called Chadwick decided there's something not quite right. And Chadwick and Bohr sort of are working at the same time, because the atoms seem to be heavier than just being protons and electrons. And he's discovered this thing called the neutron. And if we feel that neutron essentially helps to stabilize the nucleus of an atom. So while they're not charged, the protons and electrons are charged, but they're unalike, so they're attracted to each other. But the electrons are in orbit and trying to escape. So it's a bit unstable. A whole lot of forces at work there. So there's a feeling that this thing, the nuclear strong force, is actually stronger than the electromagnetic force, and the neutrons are playing a big role in that nuclear strong force, holding the thing together. These orbitals are ways of seeing how the electrons are moving. We won't go into that. That's a bit complex, really, even for extension activity. Heisenberg has this wonderful thing called the Heisenberg uncertainty theory, and he suggests that we can know how fast an object is moving, or we can know where it is, but we can't know both things. And he sort of applied that to his atomic model, and you'll see Erwin Schrödinger, the famous man of the cat. Is the cat dead or alive? Don't know. It's inside a box. We'll talk about that another day. So Schrödinger and Heisenberg combined Heisenberg's ideas here into a model that suggested that the electrons could actually, depending on the amount of energy present, be in different shells. They didn't stay in a particular shell. They were in motion all the time, trying to escape that strong magnetic force. We don't tend to teach Heisenberg's theory to students below year 10, but that's what people are using now. So I figured you should probably know it exists. We tend to stick with Niels Bohr's model because it's easy to explain what's going on. It's a very good model to explain stuff, although Heisenberg's is probably the accepted theory these days. So, subatomic atomic structure. Each atom is made of 3 types of particle. You'll find electrons, protons, and neutrons. The atomic number of an element tells us how many protons it has. But because protons are positively charged, they'll actually attract the same number of negatively charged electrons. So essentially the atomic number tells us 2 things. The number of protons that should be present and the number of electrons that should be present. The mass number tells us how heavy the nucleus is. So that's protons plus neutrons. And an atom is essentially uncharged. So it's neutrally charged. So electrons and protons should be in balance. They're not always, because we have things called isotopes. But essentially, they should be equally charged. No, sorry, not isotopes, ions. Isotopes, something else. We'll kind of talk about them too. Well, there we are, isotopes. So you may have heard of carbon-12 and carbon-14. We use that the decay from carbon-14 to carbon-12 to try and age things. So carbon-14 is carbon. It's got 2 extra neutrons. So it's heavier than carbon-12. So carbon-14 will actually decay and release those 2 extra neutrons as radiation and become carbon-12, because carbon-12 is more stable. And there's also carbon-16, carbon-15, carbon-13, maybe. There's a number of species of carbon, but they're all trying to lose those extra neutrons and become carbon-12. We know about carbon-14 because we use it for aging things. The decay from carbon-14 to carbon-12 is quite a measurable thing. And then we've got these sources of radiation. So we talk about alpha and beta particles. So alpha particles are particles consisting essentially of 2 protons and 2 neutrons bound together. and they'll be emitted from a nucleus when they're decaying. Beta particles are high energy, high speed electrons, or with a negative charge, or things called positrons that are positively charged, and they get ejected from the nucleus when things are decaying as well. And gamma rays are similar to visible light. When we get to physics, we'll talk about all this, but the visible light is one part of the electromagnetic spectrum. Gamma rays are on that electromagnetic spectrum as well, but they have a great deal more energy. So, of course, they can cause all sorts of damage. So radiation, all our elements are trying to decay back to hydrogen and helium where they started. So radiation is quite a common substance around us. You are radiating energy as well. But gamma rays become dangerous. They're things that cause harm. So they're a little bit different. So here's a little longer one, that one. Hopefully it raise a whole lot of really interesting questions for you.